Yep. Okay, welcome everybody. We're now going to start our webinar for the preparation for the exam. Now, you've submitted questions via Go Soapbox, and we've looked at them. And from inspecting your questions, we see roughly that there are three types of questions. There are questions about linear algebra, and we will address that. Most of all, it's a bit like orientation with linear algebra. Then there is a big topic, optimization. And then you have very specific, detailed questions to very specific problems. So the focus on this hour, will be that you get more structural overview, which means most of all linear algebra and optimization. So let's start with linear algebra, and let's start with the first question. So what I've seen is that you still got some issues with matrices and what to do with them and with vectors. So to give you maybe the most important thing you have to remember whenever working with linear algebra is rows times columns. That's the main thing to remember. What do I mean by that? Well, if you think of a matrix, suppose there is a matrix, and this matrix has a dimension. How we do that is, for example, think of a matrix which is filled by some symbols, and at the moment, I won't specify what is there. Could be some numbers, right? Just think of it as a big field of squares. Square stands for variable. Then this matrix has a dimension and has a number of rows and a number of columns. In this case, there are 4 columns and 3 rows, right? And if I multiply this by a vector, think about something like this. These are not zeros, just symbols. A vector. Out comes another vector. And the question is, usually, is this multiplication possible? So the first question is, and how do we multiply? We always do rows times columns, which means I always take a row here and multiply by the column there. Now the first thing you have to check is the row and column, do the sizes match? In this case, it doesn't match because the row has 1, 2, 3, 4 elements, and the column has 1, 2, 3. So this product does not exist. However, if I would add another symbol here, I would have rows of, on the left side, so to speak, rows of length 4, on the right side a column of length 4, and I could solve the equation. And what rolls out here? I have 3 rows, every row meets a column, so out comes a vector of length 3. So, which means, and that is what we sometimes also ask you, let's do it in algebraic way. It's a matrix. Again, we always write row times columns. It's a 3 times 4 matrix. The vector, again, think of row times columns, has 1 row, 1 column, sorry, it has 4 rows. Okay, I can't have an eraser here. Ha! So it has 4 rows and 1 column. That's what the vector is. So the resulting object, if I multiply the two, you recall we said then I can compute it as is of size 3 times, and the 4 cancels out times 1. And why we can do that? Because it's the same size. So the key issue is row times column. Now, you ask a bit different question. So let's go into it. It was about vectors. So think about a vector A. And again, recall all vectors are column vectors. So something like that. And think of a vector B. And we said that maybe we put an arrow here because in handwriting it's difficult to make it bold-faced. Like this. And then the first question is, what can I do with them? And it's always row times columns. So here I have a vector, 3 rows, 1 column. This has 3 rows, 1 column. So I cannot multiply them simply because the number of columns does not match the number of rows. So this doesn't work. I can't multiply this. However, if I do something here, if I take the transpose of A, and you learn what that means, it means I just interpret A now as a row vector and leave B as it is, I have a new problem, right? So if I take a new version, so to speak, now this has a dimension, has 1 row and 3 columns, and this has 3 rows and 1 column. So what is the size coming out of that? It's a 1 times 1 matrix, or it's just a number, which is, in the case, just a number. Now, and we have a name for that. This particular product, so the product of a vector transposed times another vector, we call it the inner product, and we write it this way. This is the inner product. So don't worry about the inner product. Just recall row times column, and if you apply it to a matrix and a vector, out comes a vector. If you apply it to a matrix and a matrix, out comes a matrix. And if you apply it, like in this case, to 2 vectors, out comes a number. So that's all you should remember. And if the sizes don't match, it's not possible to compute. That also happens quite often, or sometimes. So this is the key thing I'd like you to remember. So again, recall, it is like here, the magic thing is row times columns. It helps us here to determine whether it's possible to solve this problem and to only check the dimension. The same here, those matrices, vectors. Again, it helps us here to see, hey, out comes a number, which we call the inner product. Okay? So this is what I'd like to say about matrices here. The rest is just doing it, practice, practice, practice. So in case of need, row times columns. And something I just heard this morning, but probably I didn't told you in a lecture, but it might be very nice, is maybe you're still confused what a row and what a column is. So if I have a 3, 2, 1, 0, minus 1, pi, alpha, beta, gamma, because you know the Greek letters, right? Now, if I had such a matrix, I would wonder what is a row and what is a column. And what I've just learned this morning is good to remember is the row goes from left to right and the column goes vertical. So, right? Row 2 is this, and column 3 is this. Columns go this way. So, in case you wonder what row times columns, how to apply it. So this is actually the linear algebra bit I'd like to express. And I guess the main chunk of work, it's on optimization and finding derivatives and working with it. And the question you submitted was, what are the steps to find extreme values? Yes, this is actually asking, what did we do for 4 weeks, roughly 1 lecture per week for 4 weeks. So I try to give you a kind of overview of that. Another question is related to that. It says, how to determine if a point is a max or a minimum in a non-calculus way. So let's try to do this. Now, let me give you what I think is the most helpful. It depends on your level of understanding, right? So let's try to come with a framework, with a roadmap to solving this. Number 1, I have one variable. So I have something like f of x, right? Now the question is, how to optimize that? What was the algorithm? So one variable and we have no constraint. So, which means x may wander freely, right? So what was the algorithm? The algorithm was number 1. Compute the derivative. And as you know, we have many ways of writing that. We can write it this way. And what we solve is find an x such that the derivative equals 0. Or probably you prefer this notation because it's easier. And we call this find the stationary points, right? You know there can be several of them. So suppose let x1 to xn be stationary points. Yeah? Could be that you're just one, that you're several of them. What do we then do? We check their nature. So step 2, we check. So we take the second order derivative with respect to x of x, or more conveniently, we just stick to primes, and we have to ask the function for this point, what are you doing? And the question we ask is this: if I fill in my point here, there are several outcomes, the value is positive, then xe is a location of a minimum. You recall that we did the proof, why it's a minimum, right? If it's negative, xi is location of a maximum. And if it's 0, further research. We can't conclude with this information what's going on there, right? That was our algorithm. That's the algorithm if we have no constraints and we have one variable. Now, you recall that we had many examples, and we did in the lectures, what happens if you all of a sudden do have a constraint. Now, the type of constraints really is different from one variable to 2 or several. So, new picture. We stay with one variable, right? But now I have a constraint. With constraints. So what do you have to imagine? So I have a function f of x, and you recall a constraint could be x is only allowed to be bigger than 1, or 0, x is between 0 and 10, right? Those are examples of constraints. And you recall, if in this setting, we always emphasize there are boundary points, right? So how does the algorithm now look like? It's a bit different. So again, I first solve f on x prime is 0. So I find stationary points. Then I double check whether the stationary points are okay with the constraint. So this is what is new now. Does the stationary point fall in accessible values for x? For example, let's put an example. Let's see, this is our example. And suppose, example, I find a stationary point say x is 5. Then 0 is less than 5 is less than 10. So the stationary point is still in the running to make a max or minimum. However, Should it be the case that, for example, our point 5 is our solution, a stationary point, is 11, then, oh, sorry, I just wanted to have another pen color for the no, I can leave it this way. Stationary point is not a possible solution. And why is it not a possible solution? Well, because it's not allowed, it doesn't fill in this range, right? This is not in here. So in this case, you recall that we now have to start the thinking part. We have to keep good track of all candidates. So going back from the example stage, so what do we get here? We get a list of candidates which are now, what we have to check, the boundary points plus all accessible, admissible, allowed stationary points. It's quite heavy if you write it all down, but the logic is, of course, quite simple. If I'm here, and here's 0, and here's 10, and my function does something like that, we discussed that, then this would be a stationary point, and we would check the function here, here, and here. And because it's a stationary point, in this case we say it's a minimum, we can be pretty sure, because we're just a boundary point, that this is actually the solution. However, just me skip to another example. You recall something like that. A function could run this way. In this case, we find the function could actually something like this. Say this is -1. So the function has stationary points at x is -1, but think about this, only the green area is okay. We're only allowed to walk around here because the solution we are asked to, for example, maximize f on x for 1 is less than 0, less than 10, right? So we're not allowed to move to the stationary point, so we look at the function on this range here, and we have only 2 values to check. And what we do then is we compare the function values. In this case, we would say that this is the location of the maximum and this is the location of the minimum. And if you recall, we did this quite some time, several times during the lecture. Huh? Okay, so allow me to move back a little bit. So this is where we start. We close now, almost close the one variable section. So the first step is one variable, no constraint like you have here, and that is just the classical way. Derivative, stationary points, second order derivative, check the nature of the point, done. Okay? That's almost autopilot. If there are constraints, we have to think more. We have to again find stationary points. We have to double check whether the stationary point is in the admissible range. If so, that's good. Then we can check the nature of the point and argue with the value of the boundary points. If not, just look at the boundary points and by reasoning conclude where's the max or where's the minimum. Second variation. The third variation, so this is a picture. The third variation, someone asked for it. Yeah, but sometimes it said do it not in a calculus way, and so far there was a calculus way, a lot of computation. An example, I wrote it down here, and a nice example is this one. Now I give you a function f of x, and that is -2 divided by 2 plus x squared. And the question now is, do again find the extreme values of the function, but without calculus. What does that mean? It means that you look at the function in a qualitative way. So what does it mean? Now, if you look at it, you will see that the x actually, so to speak, sits in the function here. That's where the influence of the x is. Now, the function x squared has some clear properties. For example, it can hit the 0, but it never goes below 0, but it can take any positive value. Right? If I choose x big, x squared just grows. What does that mean? It means if you look at f on x, so for the smallest you can get, the smallest value you can have is for x equals 0, because what was out there, you divide it by 2. Which means f of x would leave you this. Oh, sorry for this. I need my rubber. Ha. So f of 2, the value would be, I fill my x is 0, and what I get is minus 1. This is certainly kind of boundary value. The only question is it the smallest or is the largest value, right? So let's think about it. What would happen if x would be very big? So if we fill in 10 to the power 100, something very big with many zeros. What happens? Look at the function here. So this becomes a very big number, and you divide minus 2 by something very big. So this becomes very small, close to 0, but look at the sign here. It is always negative. From that we conclude we have a function that at the point axis 2 is minus 1. So we can sketch the function a bit like that. So there is the value axis here is x, and here is f of x. So the function is for axis 0 has the value minus 1, and then it goes bigger and bigger and bigger. It approaches the value. Get a big set. What do I do now? It goes to 0. It goes to 0. So there's something like that, qualitatively, right? This is the fact that this here, this whole sentence says that it looks a bit like that, right? This is what I'll use here. And this information is what I use here, right? The combination gives me that sketch, and I conclude is location of minimum. And you recall the example in the lecture. This function has no maximum. Recall it? If I approach something and I don't touch it, it's not a maximum. So, and no maximum, right? Now, these are the 3 variations we have in one variable. There's more to come, you know. So, we have the clear thing, no constraints, first stationary point, second order condition, and fine. With analysis, with constraints, again, stationary points, boundary points, argument, fine. And the third one is without calculus, which is this kind we just discussed of reasoning. Okay, now, there's more, of course. Huh? Now we do several variables. So the story continues. It really is helpful. Probably you need a page of A3 format or something for yourself to write down the kind of blueprint, algorithm it is. That helps a lot to clarify things. Let's look at extreme values and let's do several variables. So I now have several variables and I have no constraint. right? And to make things easy, let's suppose the function is something like f of x and y, but on the record, it could be f, y, z, r, q, you know that. It could be x1 to xn, but just for me, for writing, let's stick with 2, right? No constraint. So the question is, does such a function have a max or minimum? How do we do that? Again, step 1, this is exactly like we did in the analytical calculus-based approach for one variable. We compute the partial derivatives. In this case, the partial derivatives with respect to x and with respect to y. I use this notation here because I find it really easy to write. And why do we use this? We find all stationary points. Find stationary points. So we solve, it means we solve a set of equation which is f x y equals 0 and fy. You did that a lot. You have a lot of practice in that. This is algebra, okay? Out of this results in possibly a list of solutions, of stationary points. I know you all hope for just one, but it could be actually a list. I could have pairs xi, yi for I equals 1 to, let's say, m, right? I could have several. M could be 3, 4, 5, or 1. Now, next step is, and this is now a bit different from the one variable, we have to first check whether such a point actually qualifies for having a extreme value, right? Maybe it's a saddle point, maybe it's inconclusive. And you recall that this is a bit more complex step. So let's continue. We are again with several variables, no constraint. And this is, so to speak, part 2. Now, we are in step 2, right, related to the one variable case. How does it work? You recall that we now need all higher order partial derivatives. So this is the partial derivative with respect to, I can write it out, x of the partial derivative we already had, right? The second order partial derivative with respect to y we need, and the combined one. And it's free for you to choose because for us it's always the same. It has no effect whether we first take the partial derivative with respect to x and then with y, or the other way around. But this is the input. You need it anyway. So this is the input, so to speak. It's good to have that on a separate piece of paper or somewhere on your workplace to work with it. How does it work now? Now, you recall that we have to do the following. I have a candidate, and that is xi, yi. And that has a certain value. The second order partial derivative with respect to x for this particular point has a value. So does it have a particular value, the second order partial derivative with respect to y? And then the mixed derivative also has a particular value for this particular point. And you recall that we square this one. And let's call this step 2a, because actually it has this thing we do have 2 steps. Now what can happen now? This expression can actually do 3 things. I mean, it can either be positive, it can be negative, or equal to 0. And what was it? If it is positive, we say there is an extreme value, which means the xi, yi point is either minimum or maximum. We just don't know at the moment. If it's negative, it's a, oh, that was a Dutch way of writing. Let's do this consistent. It's a saddle point, or not conclusive. Right? Those were the 3 cases. And if, now I know we continue. If it's a saddle point, so suppose, make an example. value for my point xi, yi is negative, then xi, yi is saddle point, and I'm done. Right? However, if, and this is set to be, if the condition here is, so this whole expression, if you plug it in here and you get a positive sign, then, oops, then xi, yi is an extreme point, the location of extreme point, and I check, I fill in any second order derivative, you recall that? I fill that point in, and again I can have two outcomes. It's either positive or negative, and if it's positive, then it's a minimum. On negative, it's a maximum, right? This was our overall algorithm in the case that we have no constraints. So let's look at it again. I have a part one, which is finding stationary points. And you recall it's always about stationary points. And that can give you a list of candidates. Maybe one, maybe two, maybe three. Once I have that list, those candidates have to go in a bit more detailed, so to speak, solicitation round. And that means that we do the check 2A, which means take the second order partial derivatives and decide, first of all, is it extreme value? If so, continue and check what's the nature. If it's negative, it's a saddle point you're done, otherwise it's not conclusive. So this is this algorithm, right? The no constraint. However, that is just part of this story and part of the fun because we did more, right? Now we have several variables. And we have a constraint. And to be very precise, we have not just a constraint. The constraint is something that is an inequality. I will explain to you what I mean by that and why I stress that. So let's look at this. So we have an objective function again. I just take two variables, I could use more, and we have a constraint. And the way we build a constraint, we play a little with that, is our G, but our G is a kind of double role it plays. The constraint looks something like that. We have another function, let me call it constraint function. And that's a function gxy. And the actual problem we look at is maximize or minimize f on x such that g of xy equals c, where this is some constant. Right? We did many examples of that. On the board, I recall that we could, how many boards did I fill? 5 or 6 with one of those examples. So this is a scheme, right? Okay. Now, the fact that I mentioned this here, the story that says this is, so to speak, the input, and we translate it, or we use it to model a problem, is important because especially this g function is a function, but here actually it appears in a kind of equation form. So now, how do we solve that? You probably know that. several variables and constraint, you should immediately think, oh, that's Lagrange, and you're right. So the Lagrange function becomes an x and a y and a lambda. Yeah, you know your Greek letters, of course. And here goes the objective function, minus lambda, and you recall that the constraint function goes here, minus the value of the constraint. We practice that this little blue box over here, this C, translates in this form, right? And what do we do then? Not surprisingly, step one is we find the stationary points, right? Which means, shorthand, the partial derivative with respect to x of the Lagrange function, the partial derivative with respect to y of the Lagrange function, and depending on your liking, if it be super correct, it's the partial derivative with respect to lambda of the Lagrange function. And they're all equal to 0. And you know, I mean, we practice it a lot. There is certain tricks how to do this. Always make equality for lambda, solve it, you know that, you practice that. Outcomes of this results in, you probably recall that, some relation between x and y. You recall that we have examples, for example, where I got something like, oh, 2x is y. We did many examples. So the goal of this part is that to find a stationary point, we first set them all equals to 0, and we got a simple equation. And what do we then? Insert in constraint. I haven't much room to write here. Because while we do that, this we actually didn't use. So, out of that row is the following. We still at several variables with an equality constraint, right? So, what does leave me? I'm still step 1. And out of that, I check my stationary point. Which I found by solving lambda x equals 0, lambda y equals 0, lambda equals 0. And the trick of solving that is, right, the first two with respect to x, with respect to y, you solve for lambda, you insert that in the constraint many times. Now step 2. Suppose this results in a list, right, of solution. Again, it could be many of them, an xi, yi, and suppose I have m such solutions. What do I do now? And this is where it's completely different from, just got a strange sign here on my computer. So this is completely different from what we've done for 1 or 2 variables. Now we argue differently. Step 2 would be, what is the nature of the point? And here we deviate a little bit and we argue with the constraint. And we have 2 major scenarios. So 2a, gxy of c is a closed curve. And we say so on the exam, so you don't have to see it by yourself. We say, like, we did this one old exam question you recall in the lecture, where we say, remember, this is a closed, or note, this is a closed curve. What does it mean? If it's a closed curve, you recall that was walking around, coming back. So we have to pass through the maximum, we have to pass through the minimum. What you do is you compare the objective function, so f x, y, i's. And the largest value gives the maximum, and the smallest the minimum. Right? That was one scenario. Otherwise, calls to be gxycx. Oh, sorry. Equals c is a straight line. In this case, check neighboring points. Recall we did very often in the lectures, but to just give you for 2b, typically it's like this. If I draw it, I have here my x, here my y, and if you are fantastic in drawing, you could have a 3D. Here that would be the functional value of the objective function, but I can't draw it good. So, and the constraint would be something like that. This would be the line g x, y equals c, which means a point here, x, I, y, e, is on the line if and only if for that point gxi, yi equals c. Okay? Now, our question is, I give you, we have candidates, we have those xi, yi's, what is their nature? And we always say use neighboring points, but the easy points are those points here, because, why they are easy? Because in this point I know already that the x component is 0, and in this point I know already that the y component is 0, and then it's sometimes easier to compare what is the function doing in axis y, and put it this way. Here's a function, and so the y value is m squared. In the middle is my candidate, and on the other side I have this function where the y is 0, and suppose that the x value here is a triangle, and then I ask myself, is it something like this? Then I would, so on the boundaries are bigger, or something like that. Right? In this case I would have a minimum, in that case I would have a maximum. Key point is, I just make easy points. However, maybe you're in a good mood, you want to dare something, you could also use those points, of course. It's just that we use the zeros because they're easy to find, right? That's the entire story. Okay, so this is, let me go back. Quite a story already, right? We started here. Several variables constraint equality, and equality means that the g always has the equal c here, right? Equality. And so long story, but we did more. We did inequalities. We also did, this is several variables. Inequalities. Now it's a bit much saying that we did a lot here. We more or less mentioned it, right? Because the moment I say several variables and inequalities, I can only solve that for a very limited setting. And the limited setting is that of linear programming, which means linear functions. So what we did here is, I have to come back. Yeah, I'll do this in a second. We do something like that. We say, if x times p is my objective function, And I can write my constraints in something like that a matrix A is given, it's larger than a vector C, and the x, for example, are all positive. This is now vector notation. Then I can solve this. Now, we didn't solve it, right? We just said it can be solved. What we did here is actually, we call this LP, right? We call it, this is the LP problem. And what we did address there was how to modulate, how to write down objective function or give an objective function to see what the problem is. So compared to the others, this is rather limited. Okay, now, after this kind of helicopter view, there's one thing I haven't addressed, and you probably may wonder about that. That is the role of the Lagrange multiplier. Lambda is called the Lagrange multiplier. And there was a thing we discussed that the Lagrange multiplier is linked to the solution. How was the story? The story was I have, for example, I maximize the function xy subject to gxy equals c. So I use the general setting, and we solve that, and suppose, lo and behold, we find stationary point x1, y1, and we find, so to speak, x2, y2. Two stationary points, right? That could come out of step 1. And then we put it into the consideration, and out of step 2 rolls out x1, y1 is the location of the maximum, because that's what we're looking for. Right? And no lambda here. And then there is a kind of step 3, and this step 3 only comes here now. And then we ask for an approximation. Then we typically ask, so we zoom in now on the C here. 3 is about the C. Suppose C is increased, changed, altered by some delta C. So, which means the new C is C plus delta C. And then we ask, approximate the value of the solution. So the first question is, what is the value of the solution? So this is all about location. And the value of the maximum is when I fill it in the objective function. So it's the f x1, y1, right? That's the value of the objective function. So the question in 3 is, how does this value change if I change a little bit the c? That's the big question. And then we say, because if I just put it this way, you might be tempted to do it all over again, the Lagrange, which is not what we want. We usually say approximately, and sometimes even say use a first order approximation. And what was that? So I want to know, and you recall we had this little star here. The little star was the function that directly gives me, for the constraint, the value, right? Because we said, if I'm honest, this is actually an x1 that depends on the c. Oops, sorry, it is the y1 here. Right? Let me write it a bit clearer here, otherwise you probably, this is a c, and the y1 depends on the c. Huh? The c, so to speak, this c works through until it reaches here the values. This is how the logic works, right? And we said then, oh, well, that's cool. Why not simply call it f star of c and suppress the entire solution story, make it easy. That's what we did, right? So the question is, how does, and this gives me directly value of constraint, value of the objective function. Good? Now, coming back to point 3, this should be approximated. And how does approximation work? It says use the function value you have at c plus change times. And now I would have to write here the derivative, but that is in this case the lambda value. Because, just to remind you guys, this is nothing else than the derivative, it's a derivative with respect to c of f prime, of f star c. You don't have to know this. No, put differently. You know this, so you don't have to actually write it. So the correct answer is simply this equation. And you recall we did some exercises with that, and then, for example, f star and c was given, and it can come as a variation, right? You either are asked to approximate the value or just approximate the change, which would be this part. That's it. So this is the entire story about the optimization, right? It's rather complex. So if we process this, the first thing is, how many variables do I have? Very important. The second is if several, are there constraints? Are there equality or inequality? Inequality is LP. Equality is Lagrange. And then there you go. If we do Lagrange, step 2, what is the constraint? Is it a closed path? Is it a line, right? If we just have one variable, that's a bit safer. First, second derivative, but don't forget there might be boundary points. So this is a bit what I want to say as an overview of the optimization. Any questions?
The voting on how to do Taylor approximations went up.
Yeah, because I mentioned that. Good. That's a good point because it perfectly fits with what we did so far. A Taylor approximation, and it perfectly fits with what we just had, namely that an FC, I just switch notation in a minute, is approximately a function in C plus a delta times a derivative. C, I should write C here, sorry. And if you recall, I recall from many questions you had during the lecture that it is still a little bit shaky where to develop a Taylor series and how to do this. So let's make an example, or first in a cleaner form. So I have a point x0 and call this the base point. We didn't do it this way in the lectures, but maybe it helps to do it a bit differently. Or not differently, with a little different angle. That's the base point. So my goal is approximate f on x in the neighborhood of x0. So I have a picture where I have some function, which I do not know. There is a point x0, and I approximate it. So as you experience in the lecture, approximations are not exact, otherwise we wouldn't call it approximations. So you want to make locally good. So I want to somehow be happy in the neighborhood of x0. And further away, well, okay, maybe here my approximation is not so good. But if it's here, fine. That's my question. How do I locally do this? Yeah. And how we do that? We have levels of that. The first approximation, to absolutely stupid, and we didn't actually do it, is, well, if I know nothing else, I have no information at all, well, assume everything is constant. You recall that? Just say, well, I only know my value at f0, everything is constant. That's stupid, right? You probably imagine that that's not so good. So let's make a polite blue, not red, a polite cross it out. Now, the first one gets a serious one. Now you know derivatives. So how you approximate that? You approximate it by a line. You say, hey, if I would have to draw a line to the function, and suppose the function is something like that. Let's draw a function here. A nice one. So, and you were asked to, let me see, let me do something. Okay, I just raise up my smileys and repair the figure. A bit more exciting maybe, like this. Oh, that's better. Good. Now, I want to approximate this function by a line. Then, locally, probably this would be a very good line, right? This looks good here. This looks a good line. Because close to x0, it's okay, well, later on it's bad, but what can I do? How would this line look like? Well, this approximation starts at the 0 value and then has a change. I'm at x0, so the change, so the incline of this line, you recall that inclines are derivatives, and then we have the change. You may recall that from the lecture, right? So the incline is simply this. How many centimeters to the right, how many above? The fraction is just the f prime. And the value of the approximation, I know that many of you have difficulties here. So if I put an x here, I say I'm that far away. So this is the distance. So the idea is I have this as a starting point, as a sort of zero measurement, and then ask myself, how far do I have to walk in which direction? And this goes in here. So this is, the second level was, you recall that, we can add the next derivative. And what is there to remember? We leave the first part, we add something, and now comes a magic a half. The best way to recall that is by saying that there is on the other side a squared. So somehow the half and the squared belong together. And this is the second order approximation, what we did. And now this has been something in week 3 of the lecture, and in week 5 we come back with the Lagrange, and I understand that it's a bit difficult for you guys to link all those concepts. So, for the daring now, and only for those, this is why for us, this is nothing else than this. This is why, because this is a function which is approximated by a function, in this case for the constraint C, and by a change times the derivative. That is why we call it a first order approximation. Now, it's usually not an x and usually not an f or something. I understand that. But methodologically, this is exactly what we do. The only thing why we do it for the Lagrange function is, and this is the main message, that for the Lagrange function, this is the lambda. So this is easy, no work. This is why we do this. Anything else came up?
Maybe we can give an example for a Taylor approximation.
Oh, Taylor's always nice, yes. Example. Always dangerous examples that can go terribly wrong. I need an example. It should be too easy, otherwise it's squared. What about x plus 1 to the power third? That's a nice one. It's a smooth one, nothing crazy. And I want to approximate that. And approximate at, you always can say around. And here it comes. Sometimes we write, say x is 1. But that's a bit weird because x is also a variable. So let's say at x0 equals 1. So my idea is I have a function which I do not know, and there's a point 1. And I want to approximate this function in this area. So the first is I need what is the function value in 1. And I hope I can do it. This is 2 to the power 3, this is 8. So the function is somewhere here, up, right? Well, it's 8. So what does it around this? Well, I need derivatives. So what's the derivative of this function with respect to x? Let's see whether I can do it. This is the chain rule. Oh, I have a bracket too much, right? one bracket. I'm sorry. Chain rule is 3 down, x plus 1 squared, right? That's the chain rule. And so the first approximation is, now what is the function approximately is the value in 1 plus the derivative in 1 times how far away am I from the 1. So what does it mean? I claim, that it is 8 plus, what's the value of this derivative if I plug it in? 412 times x minus 1, or, and here comes a nice point, because you also ask that, when do I have to stop simplifying things? Now this is a brilliant example. I'm just happy that I cooked it up, because is this already okay? Are we already happy here? Not really. It's correct in the way, I hope it's correct, in the way that I did my computations, but this cries for simplification, because 8, I work away brackets, let's do step by step, is 12x minus 12, and that's of course is 12x minus 4. And this is really good. So this is what we like to see, right? Obvious simplifications have to be done, while not obvious ones you can leave. But you probably see that going from here to here is something your feeling for formulas should tell you this is what I have to do, right? Also, if we want to draw the line, it's much easier to do it this way, right? By the way, if you want to do this, if you fill in x equals 0, you're somewhere here at minus 4, and the level of 12, so it got something like that. That's approximation, right? That's our function. Okay. Now allow me to erase this, because that's easier, then I don't have to write the function again. Let's do I can get used to this. Let's do the second order approximation. So I simply continue here, boldly, take the second order derivative in 1 and x minus 1 squared. On this second order derivative. What's the second order derivative? Luckily, I choose an easy function, because I can again use the chain rule, and then I get 6x plus 1, right? So I just fill things in. I already did some work. I know this is 8. I know this was 12, if I recall correctly, x minus 1, plus a half times, if I fill in here 1, what do I get? I get 2, I get 12, if I'm correct, times x minus 1 squared. Now, again, is this already good? Now, we are happy that you can apply the Taylor series, but on a second thought, you can clean this up, right? So let's clean it up. So we've got, and pretend that we haven't done the first part. 12x minus 12. Now this is 6. 12 divided together is 6 times x squared minus 2x plus 1. 8 plus 12x minus 12 plus 6x squared minus 12x plus 6. And what do we see? We see nice things happening, because the 12 plus and the minus cancel out. That's always good news, makes life easier. And those we just combine, right? So 8 plus 6 is 14, minus 12 is 2. So if I didn't make any big mistakes, it is 6x squared. Oops, sorry, I'm at the boundary here of where I can write. You can't read this, right? So I have to do something else. Sorry for this. I erase this. Oh, no, that's not what I want. Good. Let me continue. You know this from the lectures. I love to do this. Let's a bit of walk in the park. And then we have a 14, so it's actually 6x squared plus 2. Correct, right? Is that 14? Yeah. So this is what we like. Again, we had to stop. This is tech okay, and this is really okay, right? Which means here you apply the techniques, but then there is some obvious way to simplify, and please do that. And that is an example. And if you have to draw this, it's something like, again, it has to pass through this, as here it's 2, something like that. Right? It's a parabola, but that's not something we ask. Any more things we have to address?
How to do an OLS approach?
How to do it. Ha. So for the people ask me several times, so OLS is ordinary least squares. Now, the question as such is a bit difficult to answer. What is the approach? What we did in the lectures is we said that the ordinary least squares leads to the well-known regression formula, and we worked with it. So we came to equations like y equals ax plus b, and with that we worked. So the best way, if you just think ordinary least squares means those curve fitting, those regression lines, and if you go to the old exams, which we did in the lectures, you have a perfect idea what's going on. It's about modeling. We don't really solve things here.
We still have time? He says no? Yep.
Longer than an hour, but we still...
Yeah, okay. The first one here, when solving equations with matrices.
Oh, is it? Oh, diagonal numbers. Nice. So this is a question about matrices. I'll go back to matrices now. Go from okay, matrices. So the questions are following. I have to interpret a little bit what's meant here, but probably meant something like that. If I start with a matrix like this, and these are not correct numbers, I have to give an example. So please don't do this at home and solve it. I just cook it up. And you ask A, and suppose you're asked compute the inverse. Only solve something. Compute x that it can only be applied in this setting. And the B vector is, I don't know what, 1, 0, 1. Again, no guarantee for numbers. It could be just plain things. Now, what we do then is, we do this, recall that? That was the augmented matrix, right? We get this. And it's a long way. You do know always in 9 steps, because every step should transform one of the element to a 0 or 1. However, the question now is, and that is remembered very correctly, I don't always have to do this. No, that's correct. We had 2 ways of doing this. The one is that we really transform it into something like that. That's what we call the unit matrix, right? And then there comes something else. So because I do not know the answer, let's say a triangle, a square, and a heart. Because if I draw a circle, you think it's a 0, right? And then we say, so the unknown vector x, that's the solution. No, I don't want to erase that. X is solution is triangle, square, and heart. Okay? Now, then we said, that's a bit too much work because we know that it's related to solving equation. And we said, it's also okay to stop somewhere in the middle. And again, no guarantees for number. It could be that I end up here by 0, 0, 5, 0, 1, 7, 11, 1, minus 1, right? And there is a triangle on top, and there is a router and the heart. What do? I do a dagger here. Don't get any bad feelings about this, it's just a symbol. Now, I'm here. And the question is this also okay? It depends. If you're free to choose the method to solve this, that's pretty much okay. Why is that okay? Because it's called the semi-elimination, right? And this is a full or complete elimination. If you wonder, if you now think, oh, never heard that, look it back on the slides, it's all on the slides. So semi means I stop if I just have a diagonal, if I just have anything below the diagonal 0. And what was the reason? The reason was, this I do if I think of the system of equations. Recall? I can read this as actually coming from 2x1 plus x2 plus 3x2 equals 1, and the last one would be minus x3 equals 1. It's a set of equations. We did it a lot. And if you do that, this already gives you the correct answer, because this last line translates into 5x3 is dagger. Oh, it becomes a nice. So x3 is 1/5 of the dagger. And if I have x3, I can insert it in this equation, right? This is a top-down thing, where it has x2 equals, x2 plus 7 x3 equals the router. But I already know from the first part that I can replace x3 by the dagger, so this actually reads as x2 is 7, x2 plus 7 times 1/5 dagger equals the router, and I can solve x2. This is, so you work your way up. Maybe too long answer for a short question. So if it's Gaussian semi-elimination and you ask to solve a system of equations, it's perfectly fine to stop with the diagonal. They don't have to be ones, because you can work your way through. You can make it ones, but you do the work anyways. If you ask to really compute the vector in a matrix setting, you have to do the Gaussian elimination to get really a vector answer. I think we're pretty much over time already.
Okay, one last question.
Is there anything very, very important?
Yeah, the voting for this question went up.
Ah.
Maybe we can also give an example here.
Oh, that's a nice one. Yeah. Yeah, I see you guys thinking now, okay, this is about optimization. And then, oh, yeah, how do I actually compute derivatives? Okay, now the question is, how can we find the second order partial derivative? Now, I understand this, that you really mean of a function, right? Probably means something else. I don't know. So what I read here is, if I have a function like that, I'll give myself an easy life. Like this. So how do I find the partial derivatives, right? Correct me if I'm wrong. Sometimes we say that this is just a function z. Okay? And you know me, I really don't like this kind of notation, but it's out there in the world and we can't stop it. So how do I compute the partial derivative of that mapping with respect to x? And you recall the idea is that I'm living in the x world. Hey, I'm an x-man, haha. So x is my variable. And if I look at this function, it is as if the function with my x glasses on is a function that looks like this. It has a part that depends on x and the part that doesn't. So y is a constant. In this setting, treat y as a constant. And then we differentiate. And once you so click into the setting, I have no doubts that you can do this. This is 2x y squared plus ex. Now, alternatively, I already had black. Alternatively, if I do respect to y, what happens now? Now I'm living in the y world, huh? I always ask why. Then the function, the y is the argument I'm looking at. I have the blue glasses on. So everything that is green up there is just a constant. So if I differentiate, I get 2, no, I don't want to color here. Sorry, you go rubbing. So it's 2x squared y, and e to the power x is just a constant, is 0. We treat y as a constant. Now, I know from questions you have in your lectures that you say, oh, that I understand, but boy, oh boy, what do I do if I have to again partially differentiate it? For example, with respect to y, something like that. And we write it sometimes in notation as the second one as first x, then y. Now, the important point is, if you see something like this, you have to understand that it's a nested computation. It's layer after layer. So the first step is that we have this, and we simply apply this again. So it means it is a partial derivative with respect to y of what? Of the partial derivative with respect to x. And I've computed this as 2xy squared plus ey. Where do I got it from? I just looked up here. Here is it. And I just fill it in. No magic, right? I just look at my own writing. And then, what happens now? Y is the argument. I treat x as a constant, and I get 4y plus e to the power y. That's it. Okay? That's the magic. Any more things we have to address? Otherwise, that you have to practice, but I said it, I think, in the lectures already. Good. I hope, so this will become available online, you can look it back. I think when you prepare now, be clear whether you have a technical problem like I can resolve this function or a conceptual problem. I do not find my way. And if you do not find your way, use this specifically, the algorithm I try to sketch for optimization and try to pinpoint where am I, do I know what I'm doing. I wish you all success. Find a buddy, practice with someone, think of exam questions on your own, play with each other. That is usually the road to success. And I wish you all the luck for the exam. And that's bye for now.